All right. So chapter 23 has to do with real world electrics. We've kind of been building up to this at this point. Um, and so have you guys seen before those diagrams of series and parallel circuits? No? Okay, awesome. So we're going to be drawing some of those. Down at the bottom, I've got the symbols for you, right? And this is just a shorthand for electrical circuits. It just makes them quick and easy to draw for us, right? We'll talk more in a minute about series and parallel circuits, but just kind of using that little decoder. What is this symbol? Yeah, that's a battery. What are these little guys over here? They're light bulbs. Good. If I were to label these A and B light bulbs, which one experiences current first from the battery? Not necessarily. Positive is indicated by the longer line, negative by the shorter line, and so I know that's my battery there. Right, and so A will experience the current first, right? And you've already kind of seen me draw these, right? I've been using resistors instead of light bulbs. Again, which light bulb experiences current first? Yeah, light bulb A, right? Is current coming out of the top or the bottom of that battery? The top. How do you know? Yeah, because that longer line is up top, and that represents the positive end of the battery, right? And so we are using current flowing from positive to negative. Fair enough? Okay, so these symbols are on page 740 in your book, and I'm going to give you guys whiteboards, and Matt, get out a piece of paper. And so I want you to use those symbols on page 740 and draw me a circuit with a capacitor and a bulb. Matter to me. Nice job. And then hold it up whenever you're done. Yay! Right? Kind of. Good, right? And so Gabe, you did a battery and a capacitor and a bulb, right? But just a capacitor and a bulb. Okay. So give me a battery and a bulb. Good job. Good question. So I would draw a little connecting wire between them, right? And I would do 2 batteries and my light bulb. Yay! Good job. Nice work. All right. Battery and 2 bulbs. Sorry. 1 battery, 2 bulbs. Yeah, so I abbreviate my battery symbols to do that. Yeah, that's fine. Whatever works for you. Yup. And so tell me, is this any different? Are those 2 different? No, not at all. Doesn't matter. Alright. Battery, 2 bulbs at different junctions. You got this new thing, a junction. You guys are basically electrical engineers after this. Okay, that'll work. Yeah. Kind of. you got to connect to that other bulb. It's got to be connected on both sides, right? And so you could be looking at, and look at each other's because you're all right, right? Did you erase them already? Hold them up and show each other. Yeah. So those all work, right? That's absolutely fine. Those all work. All right. Battery switch and 2 bulbs. Now the location. Let me qualify a working switch that will turn lights on and off. Mm-hmm. Yep. Good. Great question. Yeah. So if there's a switch between the bulbs, then what happens? Depends. Depends, right? And so, yes, there are ways that I could put a switch in here, and it would leave one light on and one light off. However, this is not one of those ways, and we're getting there when we build circuits. I just want you to know working switch in this is before, right? Between the positive terminal of batteries and the light bulbs in the circuits that you drew. All right, battery switch, 2 bulbs, and a junction. No, just one battery, a working switch, 2 light bulbs, and a junction somewhere. Remember your light bulbs, 2 light bulbs with a junction? Good job, Ned. Put a switch in that. Kind of. Ned, hold yours up. Ned's got one way to do it. Yeah, that would work. Right. And then as soon as I connect this switch, there's current flowing to the light bulbs. They'll turn on and off. Right, when the switch is... Let me see. Ah, good question. And so let's say this is connected, right, a switch, and I put my switch here instead, right? Can current still flow through that first light bulb? Yes, it can, right? But this switch, if it's off, will current flow through this one? No, it won't. And so this is the way to have a switch between 2 light bulbs where one will stay lit and one will not. Erase all, right? Battery, switch, 2 bulbs, junction, resistor, affecting 1 light bulb. So remember, that light bulb has a resistor that affects only that light bulb. So it can't, I'll show you what it can't be, right? Which is a resistor, 2 light bulbs, right? Anything like that, because this resistor will affect both of those. Nailed it, good job. Is my mic up? Yeah, okay. Yep. Is that the same as Gabe's? Yeah? Nice. Let me see. Where's your resistor? Yeah, Hmm. And so you've got this one little light bulb, right? And then somewhere in a resistor, another light bulb, and then they connect. Yep, that works. Absolutely. All right. So, there's these kind of laws about circuits and about how electricity flows through them, right? And we've talked about junctions already a little bit, and we've even talked about this law. We just didn't give it a name before. And so this is Kirchhoff's junction law, and this says that the current flowing into a junction has to equal the current flowing out, even if it splits, right? And so let's say that I have 4 amps of current going in. What is the current in 3 and 2? Yeah, 2 amps each, right? As long as that junction is made of a similar material, we can assume that it's evenly split, right? If for some reason they were different materials, we could still have like a 3 and a 1, right? But we're going to assume uniformity here. But either way, the stuff coming in has to equal the stuff coming out of a junction. And vice versa. If I have, let's say 2 amps of current and 8 amps of current, and they're flowing in this way, well, what comes out of that? 10 amps of current, yeah, right? So this is, again, something we've already talked about. We're just giving it a name now. Kirchhoff has a few laws, and so Kirchhoff's next law is a loop law, which says that the changing voltage across a circuit equals 0. And so if my battery has a voltage difference, or we've been calling that the EMF, the electromotive force, of, let's say, 10 volts, like it's a 10-volt battery. I don't even know if they make those. I know they have 9 volts. Then I know that these 2 resistors also use 10 volts. Right? That battery builds up the voltage potential. It travels through the wires, and then it drops equivalent to the battery across the resistors. Not necessarily, no. But they add up, yeah. So I could have one resistor that uses 8 of those volts and the other uses 2. Depends on the resistance of that material. Right? As resistance increases, what happens to current? It decreases. Yeah. And so they could be equal, or they could not, but either way, I know the 2 combined equal the battery. Right? Let's imagine this little circuit over here. Let's say I have a 9-volt battery. What's the voltage drop across that one resistor? 9 volts as well, right? They can only use what is there. And so, knowing this, then, our loop law says that if the voltage of 0 is 0, then the voltage of the battery is equal to the same thing across the resistors, the voltage drop, right? I know that we're calling the voltage difference across the battery the EMF, or the electromotive force. And what is this? We learned it last class, V equals IR. There was a law, names for it. Ohm's law. Yeah, this is just Ohm's law, right? And so these are all things that we already know. But when we apply this new information, it's only kind of new, we can come up with that the current is equal to the EMF of the battery over R. Again, that's just Ohm's law, but now we're substituting the E for delta V. Does that make sense? Right, no, the voltage of the battery minus the voltage difference across the resistors has to be zero, the difference in them, because of this law. And then when I substitute delta V into Ohm's law, I can come up with the EMF of the battery divided by the resistance of the resistor is equal to the current. And just a little bit of substitution. There's two types of circuits. There's series and parallel circuits. And so a series circuit is just a direct flow. There's only one path for electricity to follow. A parallel circuit is something that contains branching or junctions, right? We usually illustrate them this way. Does it mean the circuit is physically laid out this way? No, not exactly. You know, these wires can have bends and curves and loops and different distances, but we draw the circuits very simply this way. And so what I want to do is take you guys over into the computer lab and do some virtual circuit building in series and in parallels, because there's some pretty important differences between series and parallel circuits in terms of how light bulbs use electricity in them, and as far as breaking the circuits goes. And so we're going to go explore that. To do that, you can click on this link. There's also a link in D2L under Labs. And so you guys will go log into D2L and you'll click Circuit Building. And we're going to complete levels 1, 2, and 3. This is kind of like electric field hockey. It's a lot like a game. And we're going to jot down the little trends and differences that we see at each level. Alright, so levels, let's see, levels 1 and 2 were series circuits, level 3 was parallel circuits, and so what are some of the observations that you guys have from that? Mm-hmm. Equals dimmer, so the more bulbs we had, the dimmer they got. In parallel, what's the corresponding state? If I have more bulbs, what happened? Yeah, they were all the same. So no matter if I had 2 or 3 bulbs, right, they all had the same brightness. What was something else that you noticed about series and parallel? Yeah, they're all completely dependent on each other, which is if one thing goes out, what happens? Yeah, if one thing goes out, they all go out. Why? Why did that happen? Yeah, there's an incomplete circuit. Right, and this is Christmas lights. That's the huge problem with them. Well, Gabe asked a really good question. He said, well, don't they make strings where one bulb can go out and the rest are fine? I said, yeah, they do. Those have kind of a backup device in them, in that if you look at the bulb, right, the filament can break, which will cause that light to go out, but they have a little tiny metal piece between that still allows electricity to flow through, right? And so those are the Christmas lights you want, right? You don't want your whole tree going out. In parallel, if I knock one bulb out, what happens? Yeah, one out, and it's the only out. All of them stay on beyond that because they all have a way to complete the circuit without that one bulb. They don't depend on each other. Any other things you guys noticed noteworthy of series and parallel comparisons? Why were the parallels still so bright? And Lisa asked the same question. And so I know, right, if I have a battery with light bulbs in parallel, the resistance of these two light bulbs, the voltage drop across them, has to equal the battery in some way, right? I know that because of the loop law. But if I take one out, you would think that, okay, now this one equals the battery, it should get brighter, right? And so that's where our math comes in, and I wanted you to see that because this is a really great question. And so when we look at these, we're going to talk first about series and then about parallel. We have what we call equivalent resistance, right? And this is the easiest one to think about, that if I've got two resistors, I could talk about them in terms of one resistor, right? The resistance of one plus the resistance of the other has to equal that equivalent resistance, as if there was only one. Okay. If I have a 10-volt battery here, what do these have to add up to? 10 volts, right? If I have a 10-volt battery here, what is this one? Yeah, still 10, right? And so 10 is equal to, and then if we have two resistors, it could be like 8 plus 2 voltage drop, right? Same thing. And so when we talk about equivalent resistance for a series circuit, all we have to do is add up all the resistors within that, right? The resistance of 1 plus the resistance of 2 plus the resistance of 3 on to however many we have. And if I want to talk about the current going through those, I can still use this. No problem, right? Does it matter to the current how many resistors I have? Does that change the amount of current flowing through? No, it doesn't. If I've got 1 or if I've got 12, the current is going to be the same. It's the resistance of those resistors that is different. They all add up to the same thing. Right. However, if I have parallel, what happens to the current I here at this junction? It splits, right? If I've got a current of 10 volts, right? What is the current here and here? If it splits evenly, or I'm sorry, 10 amps. Yeah, I've got 5 amps and 5 amps. That's why they're the same, right? And so that's why it doesn't matter how many I've got, right, and how many splits I've got, the current going to each bulb is the same, thus the brightness is the same. There's still a junction, yeah. And so this current is still trying, right, but it's not going to go through. Right? So where does it go? Good question. And so, let's see. Let's talk about resistance really fast. If these two have the same amount of current, the resistance thing gets a little bit complicated, right? This is still true. But what we end up doing is we can say we factor out the EMF, the voltage of the battery, and I get equivalent resistance this way. If I want to rearrange this, which is E over I, then I end up with this big factored thing down here. The E's cancel, and then this is my equivalent resistance for those resistors. Okay. Do I expect you to know all of this? No, not necessarily, right? We know this formula, we jotted that down. We know the current in Ohm's law. But the resistance, the equivalent resistance in parallel is a much, much different calculation, right? As if I had one resistor. And so Lisa, you said current is never created or destroyed. That's true, it's not, but it doesn't have to go anywhere either, right? Parallel, one of the important things to note about this is the equivalent resistance for all of the resistors is always less than any one resistor. And so if I have a 2 ohm and a 3 ohm resistor, right? What is the equivalent resistance for those two? 1/2 plus 1/3. So figure it out. Bust out the calculators. What is the equivalent resistance for those two resistors in parallel? What is it? Somebody confirm? Right? The equivalent resistance is less than any one resistor. Right? If I take this and plug it back in here, R equivalent is equal to the electromotive force over I, right? Let's say I have a 9-volt battery, right? And I know that R equivalent, delta V over I. What is the current in that system? Right. What is the 9 volts? Is that current or electromotive force? Mm-hmm. 10.8 amps. Somebody confirm? And so we use parallel circuits for a few reasons. One of those reasons is that if one thing goes out, everything else is still okay, right? The other reason that we use parallel circuits is because they draw less current. Because the equivalent resistance of everything I've got hooked into that circuit is very, very small, as opposed to if I connected them in series where they just add up. And I can't have many things on that circuit. With a parallel circuit, I can have buku things on the circuit, and it still works. And so this is what we have in our homes. This is what we have in our cars. This is what we have in our phones, right? If one thing goes out, everything else is okay. And they're able to really efficiently use the power from the battery. Oh, the current splits, yeah, sure. So the question you're asking, let's see. Let me find this. Discard. And so what you're asking is how does the brightness of that compare to a parallel? Good question. And so if I have a 10-volt battery and a 10-volt battery with, let's say, 3 amps of current and 3 amps of current, how much current is flowing through both of these? 3 amps. Right. How much current is flowing through each of these? And so you're saying if they are connected in series with the same power source, would they be brighter? Yes, they would. They would also be faultier. And because of this whole equivalent resistance thing, right? equals R1 plus R2. R equals 1 over R1 plus 1 over R2. And the inverse of that, because of this whole equivalent resistance thing, ultimately I draw less. Let me make sure I'm saying this right. I draw less current in parallel than I do in series, right? Because as the resistance goes up, what happens to current? As resistance increases, right, what happens to current? Current decreases, right? Here, my total, this is almost like the more things that I add to it, the less resistance I have in the circuit. And so I can distribute that current very nicely and evenly, right? All right. We've got a couple of devices that tell us about circuits. We've already used kind of a combination of these, but let's say we're going to use just one. An ammeter is something that tells us the current in a circuit. Current is variable I, represented by amps. If I wanted to know the current in this circuit of the current going into the light bulbs, where would I have to place my ammeter? And this is the symbol for an ammeter. Yeah, somewhere between the positive charge of the battery and the light bulbs, and so I would place my ammeter right there if I wanted to measure the current going into those light bulbs. A voltmeter, and this is the thing that we used the other day, is any device that tells us about the voltage difference across an element, and then symbol for voltmeter here. And so let's say that I want to know the voltage drop across light bulb A. How would I have to place my voltmeter to tell that? Yeah, I want to know delta V. And so you're right, I do have to have one thing here, but if I want to know delta V, kind of, I would actually have to put another lead here, right? And measure the voltage going in and the voltage coming out to get delta V. Right? And so my voltmeter would go right there. And that's what we were playing with the other day with the two little probes, right? I put one before and one after and get my voltage difference. This is what we're going to do tomorrow in lab as well, the voltmeter. Voltmeters and ammeters are frankly kind of old devices because in modern times we have what we used the other day, which is a multimeter, which can kind of do it all. And so this little thing down here, right? What do you think that measures? The unit is ohms. Yeah, and so I can measure the resistance of something, right, when I change it to measure resistance. What about DCA? And do you guys know what DC stands for? Direct current, yeah, A. And so what do you think that measures? Yeah, amps, current. Right? What about DCV? What does that measure? Voltage difference, right? And so you've got a voltmeter, an ammeter, and an ohm meter, which measures resistance, all in one. This is the modern tool. They can go between them. Right. And for today, we're going to stop there. So you've got homework. I've got a quiz that I'm giving you that's due on Friday, and so quiz due Friday. And you will have a homework quiz that opens up on Friday, due Sunday as well. In your homework, I do have conceptual questions, and so I'm going to put this PowerPoint on D2L, and these are the more advanced online circuit building, and you can use those to help you out with those conceptual questions. Right? pretty easy to use. One of them is way more advanced than we are going to use, but just find one that you feel comfortable with. That works for you. Those are 3 options. And you don't even have to use any of them. It just might help, right? This PowerPoint is on D2L, so you don't have to copy down the web addresses. You can just go in and copy and paste. Alright, and I'm here to help you with your homework. We have 15 minutes.